In this video, we do another example involving curve sketching. We've got h of x. It's a difference of two transcendental functions like this. Now we've also done other curve sketching videos. In the videos on the first derivative test and the second derivative test, in order to illustrate what it was we were doing, we graphed everything that we did. So you can look back at your first and second derivative test videos and watch some graphing there. All of those that involved the second derivative test were graphed. We looked at where the graph was concave upward and concave downward in those videos, even though we weren't always asked to use that. I wanted to illustrate the ideas by graphing the functions. Now in this section on curve sketching, they really just ask you. They say, here's your function, sketch it. You don't have a graphing calculator. All you have is your mind and all of the things that you've learned about derivatives and all of the things that you've learned about algebra to sketch this function. So the first thing we want to do for this is we want to find the domain of the function. We want to find the intercepts of the function. So where does this graph cross the x-axis? Where does this graph cross the y-axis? We want to figure out where the function is increasing or decreasing. We want to infer where the graph is concave upward or concave downward. And we want to find extrema of a function, relative mins and relative maxes. And we want to find points of inflection if there are any. And we want to find the end behavior of the function. So that's the plan. That's what we're going to do for this function throughout the rest of this video. Okay, so the first thing I want to do is find the domain of my function. And finding the domain requires looking for three things. We really have to figure out what won't work, and then we say everything else will work just fine. We don't want to divide by 0, we don't want to take even roots of negative numbers, and we don't want to take logarithms of negative numbers or 0. So when I look at this function, I'm looking for division. Am I dividing by any functions of x anywhere? No, I'm not. And are there any even roots? There aren't any, so I don't have to worry about that. And then I'm looking for logarithms. I've actually got a logarithm right here. I cannot take the logarithm of a negative number or 0. That's not allowed. So I need to figure out when this expression inside the logarithm is 0. I need to figure out when this is positive. In order to do that, I'm going to set x squared plus 2x plus 2 greater than 0. That's our domain. It's the set of all x for which this is positive. And then I need to find the x values that satisfy this. Now, there's a trick to this one. Notice that this has an x squared term and an x term. Since it has an x squared term and an x term, I can rewrite this a little differently by completing the square. So that's my plan. First thing I'm going to do is I'm going to get rid of this 2 on this side. I'll subtract 2 from both sides. And now I've got this. So I have x squared plus 2x. And that has to be greater than negative 2. Now if there's a number other than a 1 in front of the x squared, I would have to factor that out from both terms. But since there is an implied 1, the number in front of the x is called b. We're going to take half of that, that's 1, and then square it. 1 squared is 1. We'll add 1 to both sides. And then we'll factor this side and simplify the right-hand side. This left-hand side factored is x plus 1 quantity squared. And we're asking ourselves, when is x plus 1 quantity squared greater than negative 1? I hope you said all the time. The domain is the set of all x. Let me write this down. It's the set of all x such that x squared plus 2x plus 2 is greater than or equal to 0. And I was solving this inequality for x, by subtracting 2 from both sides and doing all of this. And eventually I got to this point. So my domain is the set of all x in the real numbers for which x plus 1 squared is greater than negative 1. But do you see that that's always greater than negative 1? That's a number squared. The smallest that a number squared can be is 0. If x is negative 1, we get 0 over here. But if x is anything other than negative 1, we get something positive. And a positive number is always greater than negative 1. So the domain turns out to be all real numbers because this is always true. Because this is positive or possibly 0, and if a number is positive or 0, it's definitely greater than negative 1. So the domain for h is all real numbers. Okay, so we found the domain. That was our first step. The next thing we want to do is find the intercepts if we can. I'm not sure about the intercepts on this one. It's going to be tough. We're going to maybe have to use a calculator, and that's not what we wanted to do. To find one of the intercepts, but we'll see what we can do without it. Now remember what intercepts are. If I want to find the intercepts of my graph, what I'm looking for are the points, the coordinates, where our graph crosses the x and y axes. So I have a graph that maybe looks like this. And I don't know what it looks like yet. Maybe it looks like that. But we're trying to find that point and that point. The graph crosses the y-axis when x is equal to 0. So if I want to find that point, I set x equal to 0 and solve for y. Similarly, the graph crosses the x-axis. Well, that's when y equals 0. So if I want to find that point, I set y equal to 0 and solve for x. So let's do the easy one first. I can easily substitute in x equals 0 and find out what y is on this graph. So that's going to give me the y-intercept. So we have y is equal to h of 0. So that's 7 times arctangent of 0 plus 1 minus natural log of 0 squared plus 2 times 0 plus 2. I'm replacing all of my x's with 0. And this gives me 7 times arctangent of 1. And of course a negative natural log of 2 over there. Now, arctangent of 1 is an angle. Inverse trig functions always give you angles. And the way I think about it is this. Arctangent of 1 is an angle, and it's the angle whose tangent is 1. So if we take the tangent of both sides, we get tangent of the angle equals 1. And there's a little bit of a restriction. Inverse trig functions were defined by restricting the original functions because otherwise, without the restriction, those didn't technically have inverse functions. So tangent of theta has to be 1, and there's this extra restriction. Theta, that's the value of our arctangent function, has to be between negative pi over 2 and pi over 2 radians. Or in other words, in degrees, that angle has to be between negative 90 degrees and 90 degrees. So I'm looking for an angle that gives me a tangent of 1. Well, I know that that's a 1 square root of 2 triangle, so theta must be 45 degrees. But of course, we're in calculus, so we're going to use radians. So that's pi over 4 radians. So this is really 7 times pi over 4. And we're subtracting natural log of 2. So our function crosses the y-axis at x equals 0, y equals this, and let's approximate that numerically. We get about 4.8. Okay, so our y-intercept is xy equals 0 and 4 pi, or 7 pi over 4 minus natural log of 2, which is approximately 0 and 4.8. So that's where the graph crosses the y-axis. To figure out where the graph crosses the x-axis, that's going to be a little bit harder for us. In principle, it's easy, but it's a little bit tricky in this case. I need to set y equal to 0 and solve for x. You might say, that's not too bad. Well, yeah. I'm replacing h of x with 0. But now I'm trying to solve this equation. So the solutions of this equation are the x values where 7 times arctangent of x plus 1 is equal to natural log of x squared plus 2x plus 2. Wherever that's true, like that's our x-intercept. It's kind of hard to figure out without some technology. I guess I could, what my first instinct is to use e to get rid of the logarithm, but then how do we get rid of the arctan? I'd have to use tangent to get rid of the arctangent, and so if I take the tangent of both sides, I could get rid of this, but then I've got the tangent of the logarithm of something. We can't get to the x's, they're inside these functions, so the best way to solve this equation is numerically. So I'm going to go to desmos.com and type both of these functions into Desmos, and then see where they cross. I know you guys are waiting while I type this into my computer, sorry. And it looks like they only cross at a single point. Looks like they cross at -1. And actually that makes a lot of sense. Okay, so I guess we didn't really need to look at that numerically. Let's think about how we might know that without software graphing these functions for us. 7 times arctangent of x plus 1, like that's this function. This function, if I complete the square, like we did earlier, this expression under the or inside the logarithm can be written as x plus 1 squared plus 1 if I add that 1 to the other side. So this is x plus 1 squared plus 1. Now that's well defined for all real numbers. But when x equals -1, then we're going to have the smallest possible value of this logarithm. And the smallest value of that logarithm will be natural log of 1. And natural log of 1 is 0. And it turns out that arctangent of 0 is also 0. So let's graph the two functions. 7 times arctangent of x plus 1 looks like this. The traditional arctangent graph has a range of -pi/2 to pi/2. So when I multiply it by 7, it's just going to go from -7 pi/2 to +7 pi/2. And then adding 1 inside these parentheses takes my arctangent graph and it shifts it 1 unit to the left like this. So the arctangent of x, or 7 times the arctangent of x plus 1 has this general shape. It's actually quite a predictable shape, so I didn't really need the technology on this, but I didn't think of it. So wasn't until I saw the graph on the screen I was like, of course I could graph that by hand. Okay, so we've got 7 times this arctangent of x plus 1, and it's just a shifted, vertically stretched arctangent graph. It's been moved this way. It's a little bit taller, 7 times taller. So we're good over there. Now this, you have to remember how natural log works. This is natural log of something, and excuse me, just y equals natural log of x looks like this. As x increases, natural log of x increases. So as what's inside here increases, the natural log of what's inside will also increase. Now, that also means that this function is minimized. It's going to have the smallest possible value when the number, or when the function inside it is minimized. And this is minimized when x equals -1. So when x equals -1, we get -1 plus 1, which is 0. 0 squared is 0, and 0 plus 1 is 1. So we get natural log of 1. When x is -1, we get natural log of 1, which happens to be 0. And then as x increases from there, as x gets farther from -1, either to the left or the right, it's going to be very symmetric. Symmetric about this line, x equals -1. The graph is going to grow to infinity, but very slowly, the way that natural log does. So we're going to see something that maybe looks like this. And it's going to have the same behavior on the other side. I'm not 100% sure about the sharp corner, but that's the gist, that's the behavior. Actually, it should be smooth, because this function is smooth and the natural log function is smooth, so maybe it looks like that instead, because we've got that squared function inside. Something like that. Okay, so where does this blue graph meet this red graph at -1? So when we set y equal to 0 and solve for x, we've got this, and x is equal to -1, and we know that because we know what this graph looks like and we know what this graph looks like, even though it took a little bit of tweaking and thinking through exactly what this would look like, given that y equals natural log of x looks like this. Okay. So we found our x and y intercepts. Next, we would want to find any asymptotes. This is positive all the time, so it has no asymptotes. Does not matter what x is, it's well defined, because that graph is going to look kind of like this. And so I can add it to all of these values on the blue graph, and everything's going to work out just fine. So there are no asymptotes. Now the next thing we want to do is determine where the function is increasing or decreasing, and determine where the graph is concave upward or concave downward. We want to find relative extrema, so find relative mins and relative maxes. We also want to find points of inflection, and then we'll discuss end behavior. Okay. So to determine the intervals where the function is increasing or decreasing, we need to find critical points. I'm going to find the critical points of f and then create a sign chart. A sign chart for f prime will tell us where the function is increasing and where the function is decreasing. Excuse me. So h was the 7 times the arctangent of x plus 1, and we're subtracting natural log of x squared plus 2x plus 2. Now remember our derivative rule for arctangent. The derivative of arctangent of x, we derived this using implicit differentiation. That's right. Was 1 over 1 plus x squared. We're using the same rule here, but we have to use the chain rule as well. So I've got a 7, bring that down. and then I multiply by the derivative of arctangent of something. The derivative of arctangent of a function is 1 over 1 plus that function squared, according to this rule, but then we substitute our function back in, so we substitute an x plus 1, and we multiply by the derivative of the inside. And the derivative of the inside is 1. Now over here, I've got the log of a function. Here's my inside function. The derivative of log of something is 1 over that inside function times the derivative of the inside by the chain rule. And the derivative of this turns out to be 2x, it's derivative of that piece, plus 2, and the derivative of 2 is 0. So we end up with this. We have 7 over 1 plus the quantity x plus 1 squared minus 2x plus 2 over x squared plus 2x plus 2. Now we completed the square earlier and we found that this was equal to this. So we've got x squared plus 2x plus 2 is x plus 1 squared plus 1. Now the denominators are the same, so we can subtract the numerators, distribute that negative to both terms. And that simplifies. In the numerator we've got 5 minus 2x. In the denominator we have 1 plus the quantity x plus 1 squared. Okay. So that's our h prime, and now we can set it equal to 0 and solve for x. Now, a fraction is only 0 when its numerator is 0. A lot of students want to multiply both sides by this. You can, but when you do, you're just going to get the numerator equals 0 times that denominator, so you're just going to get the numerator equals 0. So I always sort of skip that step and just say the fraction's 0 and the numerator is 0. So we solve for x by adding 2x to both sides, dividing both sides by 2. We get x equals 5 over 2, or 2.5. Okay, now we want to make a sign chart for f prime. I keep saying f prime. The function's name was h. It's impolite to call it by the wrong name. So we'll create a sign chart for h prime. Okay. So h prime is this. H prime is equal to 0 at 2.5. The numerator is 5 minus 2x. The denominator is 1 plus the quantity 1 plus x squared. No matter what x is, this is positive. So we get a positive and a positive there. And the numerator, well, that's going to depend on the value of x. When x is less than 2.5, you can pick any x value you want as a test value. I would try x equals 0. So I get 5 minus 0, which is 5. And you can pick any x value you want over here. Let's use x equals 3. 2 times 3 is 6. 5 minus 6 is negative 1. So h prime is positive on this side and negative on that side. Since I've got this sign chart, now I can state the intervals where the function h is increasing or decreasing. Okay, so h is increasing on this interval from negative infinity to 2.5, and h is decreasing on this interval from 2.5 to infinity. So it's increasing over here and decreasing over here. That's good information that we're going to need later. Now, since our first derivative changes signs, goes from positive to negative, we also have a relative extremum there. So we will use the first derivative test. To find relative extrema. And it turns out we only have one, so it's a relative extremum. So the function goes from increasing to having zero slope to decreasing. So we must have a relative max at x equals 2.5. So to find the y value, we just substitute the x value into the original function. And I think I want to use that factored form for the argument. That's the expression inside the natural log. So I replace my x with 2.5. I get all of this. And so we have 7 times arctangent of 3.5 minus all of this. That's natural log of 3.5 squared plus 1. So it ends up being 53 over 4, or 13.25. I used my calculator for the arithmetic. Now, the y value is this, but I would like an exact value. So I'll use my calculator for the numerical approximation on this as well. So we have 7 times arctangent of 3.5. And I am in radian mode, so that's good, minus natural log of 13.25. And so we get 6.46. So this, according to this first derivative test, this is a relative maximum. All right. Now we want to determine where the graph is concave upward or concave downward, and to do that we need this second derivative. So we're pretty much going to do the second derivative what we did with the first derivative. We're going to set it equal to 0. We're going to figure out where the second derivative is undefined, and we're going to put those numbers on a number line and create a sign chart for our second derivative. I think I may have forgotten to do that with the first derivative. When we set h prime equal to 0 and solve for x, we got x equals 2.5. But we didn't talk about when h prime is undefined. Well, since this is a perfect square, this is always positive except for when it's 0. When we add 1 to it, it's always positive. So h prime is always well defined, and that's nice. We're good there. Okay, so now we want to compute h double prime. So we've got a quotient, we can use the quotient rule. So according to the quotient rule, we get the bottom function times the derivative of the top function. The derivative of the top function is -2. So that's low d high minus high times d low. And the derivative of the bottom function requires the chain rule because I've got a function inside another function. Derivative of a function squared is 2 times that function times the derivative of the inside. The derivative of x plus 1 is just 1. So we're good there. And then we add the derivative of 1, but that's 0. So it's gone. So that's nice. And then we end up with the bottom function squared here. Got x plus 1 squared plus 1. All of that is squared. Don't square this and this. We're thinking of it as almost a binomial now. I've got this plus this. I'd have to write that twice in FOIL. There would be a lot more going on than just what we would get when we square this and we square that. So this is h double prime. We just need to simplify it. and set it equal to 0. See if we have intervals where the graph is concave upward or concave downward and all that. The easiest way to simplify it is to expand this expression. So I've got x plus 1, and I'm squaring it. So that's x plus 1 times x plus 1, and then I'm multiplying it by negative 2. And then over here I've got a negative 2 times the quantity 5 minus 2x times x plus 1. When we FOIL, first this times this, we get first times first is x squared, outer times outer is x, inner times inner is another x, so I've got 2x, last times last is 1, 1 plus 1 is 2. And I multiply all of that by negative 2. Over here I've got a negative 2. And I multiply these together. First times first is 5x, outer times outer is 5, inner times inner is negative 2x squared, last times last is negative 2x. We're dividing all of that by x plus 1 squared plus 1 quantity squared. I'm not expanding the denominator because this is always positive and it's not going to affect my signs in my sign chart. I need to figure out where h double prime is 0. In order to do that, I need to simplify this so that I could set the numerator equal to 0 and solve for x. So that's why we're doing this. That's where we're going. I think I want to look at that as a term and that as a term, and I want to factor out this negative 2 that they have in common. So I've got negative 2 times some quantity, all divided by this. Negative 2 times x squared plus 2x plus 2 gives me that first term. Negative 2 times all of this gives me the second term. So I've got a minus 2x squared. 5x minus 2x is 3x. And then we have a 5 there. So I have negative 2 times this. X squared minus 2x squared is negative x squared. 2x and 3x are 5x. And 2 plus 5 is 7. I could factor out a negative 1 from this polynomial. So I've got 2 times x squared minus 5x minus 7 all over this. Whew. Okay, now I don't know how x squared minus 5x minus 7 factors, if it even does. So I think I'm going to use the quadratic formula to figure out where h double prime equals 0. It doesn't factor very easily or nicely. So it makes the most sense, if I'm trying to set this equal to 0 and solve for x, to just use the quadratic formula because it's a quadratic function. Again, I've got this divided by this equals 0. So if I multiply both sides by the denominator, I just get the numerator equals 0. Which makes sense because the only way a fraction is 0 is if the numerator is 0. And we can divide both sides by the 2. We get this. Okay. So now I identify A, B, and C. A is the coefficient of x squared, B is the coefficient of x, C is the constant part. So x is negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So this is negative b is negative 5, plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. Okay, so we get 5 plus or minus the square root of 25, and negative 4 times negative 7 is 28. We're dividing all of this by 2. So you get this sort of ugly number, square root of 53 over 2. Man, okay. So we have two points, two x values that potentially give us a second derivative of 0, but they're these irrational values. That's okay. Let's figure out what that is approximately, and then let's figure out what this one is approximately. Excuse me. So I have 5 plus the square root of 53, and I'm dividing it by 2. So that's about 6.14. And then in the second x value is 5 minus the square root of 53, and I'm dividing it by 2. So I get negative 1.14. Did I do that right on the first one? I think I said divided by 4. Yeah, it was right. Divided by 2. Okay, so those are my two critical values, or excuse me, the two x values that cause my second derivative to be 0. So now we're ready to make a sign chart for the second derivative. I guess I didn't write this step down. We set h double prime equal to 0 and solve for x. Just using the quadratic formula. And now we create a sign chart for h double prime. So h double prime is 2 times the quantity x squared minus 5x plus 7, or excuse me, minus 7, all divided by the quantity x plus 1 squared plus 1, quantity squared. Now I've got one critical value, that's 2 minus the square root of 53 over 2. It's not a critical value. It's an x value that causes the second derivative to be 0. Sorry. And then I've got another one over here, and this one is approximately negative 1.1, and this one is approximately 6.1. So we want to pick test values for these two functions on these three intervals. This is positive all the time. It doesn't matter what x is. Now this is actually a parabola facing up, so I know it's going to be positive, negative, positive, but let's just confirm using our test values. So pick something to the left of negative 1.1. Let's try negative 2. So we've got negative 2 squared minus 5 times the negative 2 minus 7. And you get 7, you multiply that by 2, it's still positive. So h double prime is a positive over a positive, it's positive there. And then between negative 1.1 and 6.1, the easiest test value is 0. So we'll just get 0 minus 7 is negative 7. Negative 7 times 2 is negative 14. A negative divided by a positive is a negative. And then at x equals something larger than 6, say 7, we're going to have 7 squared is 49, minus 5 times 7, minus 7. And you multiply that by 2 and you get 14. So we have a positive over a positive is a positive. Okay, so we created a sign chart for h double prime. What does that tell us? Well, remember it's h double prime, so the way we interpret it is whenever the second derivative is positive, that tells us concavity. When the second derivative is positive, it's concave up. When the second derivative is negative, the graph is concave down. So now we can state the intervals where the graph is concave up or concave down. I'm not going to write it out over there. The graph is concave upward on this interval and this interval. So that's negative infinity to 5 minus the square root of 5 over, or square root of 53 over 2, which is approximately this. And it's concave upward on this interval as well. 5 plus the square root of 53 over 2 to infinity. So that's approximately 6.14 to infinity. And the graph is concave downward here. And I'm just doing this over here because I'm running out of space. It's concave downward on 5 minus root 53 over 2 to 5 plus root 53 over 2. So it's approximately negative 1.1 to 6.1. Okay. And remember, any points in the domain where the function changes concavity represent points of inflection. So these x values correspond to points of inflection. These are x coordinates of the points of inflection. So to find the corresponding y values, we would substitute those into the original equation and get the y coordinates of the points of inflection. So I think we've got enough to graph this thing now. Let's state our points of inflection. Our x's are 5 minus root 53 over 2 and 5 plus root 53 over 2. And we want to substitute those into this function. Okay, so I think I'm going to enter all of that into my calculator. And these are going to be approximate. So we have 7 times the arctangent of x, which is, open parentheses, 5 minus square root of 53, close parentheses for the numerator, divided by 2 plus 1. That's the 7 arctangent part, minus natural log of, open parentheses, 5 minus root 53, close parentheses, divide by 2. Actually, I think I need some other parentheses over here. So that's our x value. Now we need to add 1, square that, add 1 to that, and then close parentheses for the logarithm. So we get about negative 0.99 approximately. Now you want to do the same thing, but you want to change all of those negative square roots of 53 to positive square roots of 53. So we'll have 7 times the arctangent of 5 plus, open parentheses, 5 plus root 53, close parentheses for the numerator, divide by 2, add 1. So that gives me this piece, and we're subtracting natural log of, open parentheses, for the x plus 1 squared, open parentheses for the numerator of the x, 5 plus root 53, close parentheses for the numerator, divided by 2. That's x plus 1, close parentheses for this guy. You want to square it. Then add 1 to that, close parentheses for the logarithm. I know there's a lot of parentheses there. So you get 6.07. And the x values, the approximations for those x values were negative 1.14 and 6.14. Okay, so we've got points of inflection, we've got a relative max of approximately 6.46, and it occurs at x equals 2.5. And we know that the function is increasing on the interval from 0 to negative infinity to 2.5. And we've got these points of inflection, also those x values that we want to add to the number line. So it's increasing here and it's increasing here. And then it's decreasing from 2.5 to infinity. So it's decreasing here and decreasing here. And then from what we calculated with our second derivative, the graph is concave upward here. Excuse me. The graph is concave downward in here. And the graph is concave upward over here. Okay. All right. Now we weren't asked for this, but one thing that I also like to find generally is end behavior. We've got points of inflection, we found extrema, and I'd also like to know what the end behavior is. Well, arctangent has a range of negative pi over 2 to pi over 2. So when I multiply by 7, the range is negative 7 pi over 2 to 7 pi over 2. But then I'm subtracting something from it that's slowly growing to positive infinity. So I'm subtracting something that's going to infinity. So the end behavior of this is going to be dominated by this because this part is bounded and this part isn't. This is going to infinity and I'm subtracting it. So the limit as x goes to positive or negative infinity of the function, and I think the original label was h of x, its original name, that's going to be negative infinity. So I want to keep that in mind, and I know that again because this is bounded and this one's going to infinity very slowly. So I'm subtracting something that's going to infinity, so the whole thing is going to negative infinity. Okay, that should be enough to help me graph this. So let's graph it. Here's x equals negative 1, x equals negative 2, x equals 1, 2, 3, 4, 5, 6, and 7. And I'm just going to go out to 7 because my points of inflection are at 6.14, and all the interesting x values are right here, negative 1.1, 2.5, and 6.14. And maybe I'll go out to x equals 8. Okay, and let's plot some of these points. We have a relative max of approximately 6.46 at x equals 2.5. So at 2.5 we get about 6.46. That's my relative max. And at x equals negative 1.14 and y equals about negative 1 as well, we have a point of inflection. And at this point, x equals 6.14, y equals 6.07, we have a point of inflection. Okay, so we're told that the function is increasing and concave up at first on this interval. So I know it goes to negative infinity, but maybe it's going like that. Because remember how the concave up graph looks. It looks like that. If it's increasing and concave up, it's like this side. So it's going to have that general shape. Now on this interval, from this point of inflection to this point of inflection, the graph is concave downward. It's increasing and concave downward on this side and decreasing and concave downward on this side. So concave downward graphs look like this, and that change happens at 2.5. So it's increasing and concave downward until I get here, get to be right there. And I guess, we could substitute. I think we did find our x and y intercepts, didn't we? When Y is 0, x is -1. So that is the x-intercept. And we found the y-intercept was this, 0 and about 4.8. Okay, so we got that point and that point. And I want my function to be increasing and concave downward. Until I get there. And then over here I want it to be decreasing and concave downward. And I'll just make my point a little bit lower so that I can do that. It's supposed to be concave downward. It's not, it doesn't look very concave anything. It looks like a straight line, but it's supposed to be concave downward. And then at the end, it's concave upward and decreasing. So if a graph is concave upward and decreasing, it looks like that half of the concave upward graph. So it's supposed to be kind of concave downward, and then it switches. It's kind of hard to draw. I didn't do a very good job. It's supposed to be concave upward and decreasing like that, but it's going to negative infinity. So this is my somewhat horrible graph of our function, but it has the right y-intercept, it has the right x-intercept. It's got 2 points of inflection. It's concave up here, then concave down here, then concave up over here, and it's increasing until we get to this point, and then we have our relative max. And then it's decreasing over here, even though that point looks a little funny. Didn't quite work out in my graph. But that's the idea, guys. So we use what we know about domain to graph the function. We find the intercepts of the function. We figure out where the graph has asymptotes if there are any, and it turns out this one didn't have any. Then we use the first derivative to figure out where the graph is increasing or decreasing. And we use the second derivative to figure out where the graph is concave upward or concave downward. Then we've got the first derivative test that will allow us to determine if if we've got relative extrema, so relative mins, relative maxes. And then we look at the concavity. We have our sign chart for concavity. Does the graph, we ask ourselves, does the graph change from concave upward to concave downward at any points? If so, we call those points of inflection. And this is not requested by our textbook author, but I think it's important too. In order to get some sense of how the function behaves as x goes to positive or negative infinity, might look at limits, those infinite limits as x goes to positive or negative infinity to fill out the ends of your graph. Now this one's not perfect, but that's the idea. Concave upward, concave downward, concave upward, increasing, decreasing, and we've got a couple of intercepts right there.